The last example to a solution to the time-independent Schrödinger equation that we're going to see in this chapter is the finite square well. We've seen the infinite square well. That was a potential that diverged to infinity for particle positions outside of certain region, 0 to A. The finite square well is analogous, except the potential does not diverge to infinity. It only goes to a finite value. The potential overall that we're going to look at is defined like this. There's some region from minus A to A where there is a well in the potential, some negative V0 value for the potential. At regions outside, greater than A or less than minus A, the potential is 0. We can expect solutions that look more or less like the sorts of things that we've seen. Suppose we had some energy level here. If this was the energy level and we wanted to know what the wave function might look like, we expect the lowest energy wave function to look something like this. In regions where the energy is above the potential, your wave function curves towards the axis, and in regions where your energy is below the potential, it curves away from the axis. In order to have things that are normalizable, we have to have our wave function come down and just barely join the axis. And you get states that look sort of like this. Curving shape joining with two other curving shapes that merge in smoothly with the axis. We know from our discussion of boundary conditions that at these boundaries here, the wave function itself will be continuous, there will be no jumps in the wave function, and there will be no jumps in the derivative of the wave function either. So that's what we expect to find. In the case of the infinite square well, there were an infinite number of states. We may find a similar behavior for this, but you wouldn't expect there to be an infinite number of states to remain bound within the well, since every time we raise the energy, the state becomes closer and closer to a scattering state that is not bound. Well, let's see what these bound state solutions actually look like. The general solutions that we're working with, we have three regions. We have a region to the left of the well, a region in the center of the well, and a region to the right of the well. So let's say this is minus A and this is A in some imaginary x-axis to this panel. For x less than minus A, if we're looking for a bound state, we know the energy is less than the potential. For minus A is less than x is less than A, we know the energy is greater than the potential. And for x greater than A, we know the energy is back to being less than the potential. So those are the sorts of solutions that we're working with. The time-independent Schrödinger equation, regardless of region, and I'll just write it on the bottom here since I'll probably have space, is minus h bar squared over 2m psi plus v of x psi equals e psi. So if you consider this as our Schrödinger equation, regions where the energy is less than the potential, we can rearrange this, and it's going to end up looking something like the second partial derivative with respect to x of psi is some positive number times psi, where the positive number here is essentially the energy being negative added to the potential energy being positive when we take care of the signs and rearrange our constants. What our equation will look like, if we're going to write it this way, the second partial derivative of psi is equal to some constant which I'll call k squared psi. We've seen solutions like this before to the for the bound states in the delta function potential, for example. K here is defined to be the square root of minus 2me over h bar squared. Let me move the h bar outside of the square root here and just leave it as h bar in the denominator. You've seen constants like this before, and this looks a little strange, like we're taking the square root of a negative number, but keep in mind here that e itself is a negative number. So we have a negative e, we're multiplying it by a negative 2, so we have a positive number inside the radical here. So k is a real positive number. The general solutions we get to equations like this, psi of x is equal to a e to the minus kx plus b e to the kx. This now being for x's which can be potentially large and negative. If we're going to have something normalizable, we need the wave function to go to 0 for large negative x's. That means we have to have a equals to 0 here. we have to be able to throw out this term, because if I plug in some large negative value for x, I'll get a large positive value for e to the minus kx. So the overall solutions we're looking at here in this region look like b e to the kx. We don't know anything about b, we don't yet know anything about k other than its definition in terms of the energy. In the central region, we have something slightly different. We have the energy being greater than the potential. What that means is that our Schrodinger equation is going to look like a second partial derivative of psi being equal to some negative number times psi. The way I'm going to define this, the constants that I'm going to define in this region, will make it look like the second partial derivative of psi is equal to, and I will call this constant minus L squared psi, where L squared now is E plus V naught. The potential in this region is minus V naught in this region. E plus V naught 2m over h bar squared. That's the constant we get under these circumstances. And this is our Schrodinger equation. Second partial derivative gives you minus some number squared times the wave function itself. You know the solution in this region is going to look like psi of x is equal to c sine Lx plus d cosine Lx. We can't really say anything more about this region because both sines and cosines obey this partial differential equation and are normalizable. So we don't know anything about whether we have c or d yet. We'll come back to that in a moment. Our third region here for x greater than a looks very much like our first region for x less than negative a, and the answers you're going to get are the same. The general solution, defining things exactly the same as we did here, is going to give us psi of x is equal to f e to the minus kx plus g e to the kx. Where now, if we want things to be normalizable, we have to say g is equal to 0, since e to the kx is going to blow up as x goes to positive infinity. Our overall solutions then in this region are going to look like f e to the minus kx. This is our general solution for normalizable bound states for this finite square well potential. The next step I'm going to make requires you to think back to an activity we did earlier. The activity was to consider what we knew about the solutions to the time-independent Schrodinger equation for a potential that was even. If I go back a slide, our potential here is very much even. V of x is equal to V of minus x for all x's. We have an even potential here, we have those results. And one of those results was that if we had an even potential, we could write the wave function as either being even or odd. So, knowing how the Schrodinger equation behaves here for this even potential, we have some freedom. We can choose our wave function to be either even or odd, and that allows us to make some relationships between these constants. We have b, c, d, and f, and k being our unknowns. And we're not going to get enough boundary conditions unless we make some additional statements. So the first thing I'm going to consider is what if psi is even? We expect our lowest energy state, going back a slide, to look something like this. This would also be an even function, so if we're going to consider even psi, we should be able to find our lowest energy state. By combining these general solutions, we should be able to, well, come up with relations that give us not only the behavior on the boundaries between these regions, but also enforce the even nature of psi. So what does that look like? If we're going to have an even solution, our solution in the central region, psi of x, psi of x was equal to c sine Lx plus d cosine Lx. Well, if we're going to have an even function for psi, we can't have any sine term. So the first thing we know on the basis of it being even is that c is equal to 0. The second thing we know was that our solution on the left, the region for x less than minus a, psi of x was equal to b e to the kx. Whereas on our right-hand side, for x greater than a, we knew our solution psi of x was equal to f e to the minus kx. If we're going to have an even solution here, we have to have a relationship between these two cases. If x is large and positive versus, say, x is large and negative. If I'm going to have equality there, I have to have b equals f. So those are the conditions that we get from assuming that our wave function is even. We'll assume the wave function is odd later and see what other conditions we get. But for now, you know what your functions look like. You have these relationships between c being equal to 0 and b being equal to f coming from the wave function being even. Let's see what our boundary conditions can tell us. We have two boundary conditions. One is that psi is continuous. What that tells us, for instance, if I look at the boundary here between the central region and the x greater than a region, is that if I plug in the boundary, x equals a here, for x in this equation and for x in this equation, I have to get the same answer. So that tells us that f e to the minus ka is equal to d cosine La. The other boundary condition we have is that the first partial derivative of psi with respect to x is also continuous. What that tells us is we can take the first partial derivatives of these things, and they will also, and plug in the value x equals a, for instance, and that will also give us an equality. So if I take the first partial derivative of this with respect to x, I'm going to bring down the minus k, and I'll get minus k f e to the minus ka when I plug in x equals a. The right-hand side of my equality then comes from evaluating the first derivative of this expression at x equals a. And what you get for that, when you take the first derivative, you're going to pull out the L, essentially, and we will have the derivative of cosine being minus sine. I'll have a minus L d sine La. There's still quite a few unknowns. I still have f, I still have d, I still have k, but one nice feature of this is that I can eliminate a lot of these unknowns by dividing these equations by each other. So I'm going to do that. I'm going to divide the second equation by the first, and when you get that, you do that division, you get minus k. The f e to the minus ka cancels out in the division. I've got a minus L here, and the d's cancel out, and I've got sine La over cosine La, which is the tangent of La. So the equation that we have as a result of applying our boundary conditions is minus k is L times the tangent of La, where, just for the sake of completeness, k is defined to be the square root of minus 2me over h bar squared. Most of the time I brought the h bar squared out of the square root. And L is defined as the square root of e plus v naught 2m over h bar squared. The constants have the identical units, and they relate the energy of the wave function to the potential. What we're interested in now is how to solve that equation. And it's a doozy. The definitions we're working with are k squared is minus 2me over h bar squared. L squared is equal to 2m over h bar squared e plus v naught. And the equation we're trying to solve is essentially k over L equals tan of La, the tangent of La. If you make some additional definitions, you can actually make some nice transformations. The first definition is that I'm going to call z La, the argument of my tangent here. I'm going to call z. What I have for this, if I substitute in the definitions of L, and L in this expression, z squared is equal to 2ma squared over h bar squared e plus v naught. where, keep in mind, e here is a negative number that has smaller magnitude than v naught. If you figure out what k over L is here, substituting in the definitions of k and L, you get the square root of minus 2me over h bar squared divided by essentially what appears in the denominator. The definition of L and the definition of z are very similar. The only difference is the a squared here. Essentially, this is z squared over a squared. If you go back, manipulate your expression for z to solve for the energy, substitute in for the energy in the numerator here, what you end up finding after doing some algebra is that this is equal to defining a new constant z naught squared over z squared minus 1, where z naught, that new constant squared, is defined to be 2ma squared v0 over h bar squared. That means the equation that we're actually working with, we haven't really made that much progress towards solving it, but we have transformed it into a form that's easier to reason about. We have the tangent of z is equal to the square root of z naught squared over z squared minus 1. Keep that equation in the back of your mind. We'll come back to it in a moment. First of all, to check your understanding, I want you to work through the steps that lead to solutions for odd psi of x. If psi of x is odd, you can go through exactly the same reasoning that we went through over the last two slides to figure out what the odd solutions look like, what the constants have to be in our general solutions to enforce that psi is odd, and what the boundary conditions then give us for the continuity of psi and for the continuity of the first derivative of psi. What you should end up with at the end of this is an expression that looks very much like the expression we got on the last slide. What we got there was k equals L tan LA. For the odd solutions, you get k equals minus L cotangent of LA. These are, unfortunately, transcendental equations that don't have a particularly nice solution. There's nothing that we can really do other than solve these things numerically. What's nice about this is that I can solve it graphically. For instance, here is a simulation of or a plot of these solutions. I'm plotting the tangent, I'm plotting minus the cotangent, and I'm plotting the right-hand side of that equation, the z naught squared over z squared minus 1, all square rooted. If I plot the left-hand side versus z, and the right-hand side versus z, and I have intersections, that means that I have a solution. So the red curve here is what I get for the tangent. That was what I got for my even solutions. The green curves here, this is minus cotangent. That's what I got for the odd solutions. And the blue curve is the right-hand side. I have a slider here that I can use to tune the effective depth and width of the potential well. Small values of this slider refer to small values of the depth and or narrow values for the width. And if I have a small value here, my right-hand side, the blue curve, only intersects a single branch of the red curve. The red curve is tangent, which is what we got from our even assumption. So if we assume that psi is even here, we get an intersection. That means the only solution we have for this particular value of our effective width is, well, right here. It means we have only a single solution, and it's even. And this is the solution that we drew back at the beginning when we were trying to figure out what this solution might look like. If I increase the value of this slider, I'm effectively making the well deeper and or wider, and you pick up a second intersection, this time with the green curve. That's referencing cotangent, which is what we got when we assumed that the wave function was odd. So if I keep increasing the slider here, you can see what happens. This blue curve migrates to the right, gradually picking up more and more solutions. Here we've picked up a second even solution for a total of 3 total solutions, even, odd, and even. Here we pick up another green solution. And if I go all the way to the end here, this is just the end of my slider. There's nothing to prevent me from making the well deeper and deeper and deeper, wider and wider and wider. But for this particular value of that slider, this is essentially the value of z naught. we have 6 solutions. A lowest energy even solution, next highest odd, next highest even, then odd, then even, then odd, for a total of 6 bound state solutions for this particular well. So graphically, we can get a feel for how many bound states there are at a particular energy level. I can go and plug in the particular values of the depth and the width and the mass of the particle in Planck's constant and figure out, oh, in this case I have 4 bound states, 2 even and 2 odd. A couple of limiting cases are especially interesting here. First of all, we expect that if we have a very wide, deep well, we should get something similar to what we had for the infinite square well. Going back to my slider animation on Sage, for instance, if I make my effective width and depth of the well as large as possible, you can see what happens. The blue curve migrates to the right, and it's going to keep sort of migrating to the right as I make the well deeper and deeper and deeper. So these intersection points here, where I have my solutions for z, are going to become closer and closer and closer to these half-integer multiples of pi. This first intersection is actually quite close already, but if I make the well infinitely deep, it's going to get even closer and closer and closer to pi over 2. Likewise for this, we'll become closer to pi. This intersection will become closer to 3 pi over 2, etc. So, if I have z naught large, you get many bound states, and they occur at values of that z parameter equal to n pi over 2, where n is now 1, 2, 3, going up to infinity. This is, of course, a very, very limiting case. But if you substitute in what we knew for our value of z, you can find what this gives you is that E sub n plus V naught is equal to h bar squared n squared pi squared over 4, I'll write it this way, 4 times 2m a squared. This looks very familiar. It's the right-hand side here is the formula for an infinite square well with width 2a. It's not the infinite square well formula exactly because we have this additional factor of 4, but otherwise it looks very similar. The left-hand side here, the energy of the nth state plus V naught. The energy of the nth state now, keep in mind, we're defining the potential well relative to 0 now. So if this is V of x is equal to 0, and this is minus V naught, what we're looking at here is the distance between the bottom of the potential well and the energy level. So this is essentially the energy level relative to the bottom of the well. Looks exactly like what we got for our infinite square well. So this is good. The other limiting case I'd like to consider is a shallow, narrow well. What this looks like back in our slider case is if I move the slider all the way to the left, I'm making the well very narrow. You can see the blue curve for my right-hand side for very small values of z naught is going to bring this all the way effectively down to 0. But we always do have that lowest energy state. We will only have one bound state, but we will always have one bound state. And it's going to be even. And that's more or less what we drew back at the beginning. That was our potential, and our wave function looked something like that. You can always have wave functions that look like this, no matter how shallow and narrow your potential well is. So those are our limiting cases. We can reproduce our infinite square well results, and we always have at least one bound state. But overall, the actual shapes of these and the actual energy levels they have are difficult to calculate. The only way we were able to make any progress is by doing things graphically. That concludes our description of the bound states for the finite square well. Here. If this was the energy level and we wanted to know what the wave function might look like, we expect the lowest energy wave function to look something like this. In regions where the energy is above the potential, your wave function curves towards the axis, and in regions where your energy is below the potential, it curves away from the axis. In order to have things that are normalizable, we have to have our wave function come down and just barely join the axis. And you get states that look sort of like this. Curving shape joining with two other curving shapes that merge in smoothly with the axis. We know from our discussion of boundary conditions that at these boundaries here, the wave function itself will be continuous, there will be no jumps in the wave function, and there will be no jumps in the derivative of the wave function either. So that's what we expect to find. In the case of the infinite square well, there were an infinite number of states. We may find a similar behavior for this, but you wouldn't expect there to be an infinite number of states to remain bound within the well, since every time we raise the energy, the state becomes closer and closer to a scattering state that is not bound. Well, let's see what these bound state solutions actually look like. The general solutions that we're working with, we have three regions. We have a region to the left of the well, a region in the center of the well, and a region to the right of the well. So let's say this is minus A and this is A in some imaginary x-axis to this panel. For x less than minus A, if we're looking for a bound state, we know the last example to a solution to the time-independent Schrodinger equation that we're going to see in this chapter is the finite square well. We've seen the infinite square well. That was a potential that diverged to infinity for particle positions outside of certain region, 0 to A. The finite square well is analogous, except the potential does not diverge to infinity, it only goes to a finite value. The potential overall that we're going to look at is defined like this. There's some region from minus A to A where there is a well in the potential, some negative V0 value for the potential. At regions outside, greater than A or less than minus A, the potential is 0. We can expect solutions that look more or less like the sorts of things that we've seen. Suppose we had some energy level times psi, where the positive number here is essentially the energy being negative added to the potential energy being positive when we take care of the signs and rearrange our constants. What our equation will look like, if we're going to write it this way, the second partial derivative of psi is equal to some constant which I'll call k squared psi. We've seen solutions like this before to the for the bound states in the delta function potential, for example. K here is defined to be the square root of minus 2me over h bar squared. Let me move the h bar outside of the square root here and just leave it as h bar in the denominator. Energy is less than the potential. For minus A is less than x is less than A, we know the energy is greater than the potential. And for x greater than A, we know the energy is back to being less than the potential. So those are the sorts of solutions that we're working with. The time-independent Schrodinger equation, regardless of region, and I'll just write it on the bottom here since I'll probably have space, is minus h bar squared over 2m psi plus v of x psi equals e psi. So if you consider this as our Schrodinger equation, regions where the energy is less than the potential, we can rearrange this, and it's going to end up looking something like the second partial derivative with respect to x of psi is some positive number